So welcome. This is the section on capacitance. A capacitor is a type of electronic device. There's capacitors which are usually given the symbol of C, so capacitance would be capital C. There's inductors which have a symbol of L. I is used for current. And there's resistors, and they're usually designated by R. To make things a little bit more interesting, capacitors are in units of farads. Inductors are in units of no. Inductors are in units of Henrys. Sorry, just blanking out there for a minute. And resistors are in units of ohms, which is the upside down horseshoe symbol. Just so you think about it, before we dealt with charge, which was in units of coulombs. Can you see a problem? So I can't tell you how many times people look at C and think it's the unit for charge when in fact it's the symbol for capacitance and vice versa. So you gotta really, we ran out of letters a long time ago, and so we're reusing things, you know. Sometimes people they'll do a curly C for charge, and they'll do a Roman C for capacitance, but they'll try and make their symbols look a bit different. That's your choice, as long as it's recognizable, I don't mind. Okay, so watch out for that. Capacitance is a device which stores charge. It's basically like two big parking lots. And so we have a plate, and we have another plate, and we somehow drive charge, positive charge on one, which is negative charge on the other, and we end up with a whole bunch of positives, and we end up with a whole bunch of negatives. Okay. We don't particularly need to store charge. We can use a battery, and a battery does more than storing charge. It kind of like separates charge electrochemically and gives me all the positives I could want at one terminal, all the negatives I could want at another terminal. And I can use that as an energy source, and it contains a lot more energy than a typical capacitor can store. So from an energy storage point of view, a capacitor is it's not going to be your first choice. There are some specialized cases where you might want to store energy for just a short period of time, and then a capacitor can be really nice. You can charge it up, you can store the energy, then give it back. If you want just a temporary place to put energy while you're doing something, you might use a capacitor for that. Or there could be a situation where, you have something that's a horrible environment where putting an electrochemical cell in might be a real pain. But again, you can't store the energy for very long in a capacitor. It just doesn't store for very long. The other reason why you might deliberately make a capacitor is because it is a type of device which displays transient effects. And what I mean by that is it basically it does not respond instantaneously to voltages that you apply to it. So it can smooth out sudden changes in a voltage. That time-sensitive behavior is kind of quite useful. And we can think of a capacitor as being a high-pass filter. If you have a rapidly changing signal, it lets it through. If you have a DC signal, it stops it. So if I have, for example, if this is voltage and this is time, if I have a very small signal on top of a very big background, and I want to amplify that signal so that I could maybe play it through a speaker, maybe it's music, but it's on a very high background. If I just amplify it, I have a huge problem because to get the signal big, it gets a very big voltage. If I want to make this factor of 2 times higher, then yeah, that's 2 times higher, but this is 2 times higher. It's a real pain. So what I can do is I can put this through a capacitor. What it will do is it will basically get rid of all that DC. So I end up with the same, I'm drawing it too big, you end up with the same small signal without a background. And then I can amplify it 10 times and I get a much bigger signal. So it's great for that. So you use an awful lot of capacitors in what's called decoupling capacitors for that kind of behavior. And the other time you use capacitors, for example, is in a specific tuning circuit, like for a radio or a television or a cell phone, where you want a whole bunch of different signals to be distinguished by their frequency, but you want your radio to pick up the one frequency that you want. You might have 10 radio stations locally. Your radio receiver picks them all up. It doesn't ignore them. Well, it doesn't not pick them up. It picks them all up. But by using a tuning circuit, you limit the circuit's response to the high frequency signals, and you limit the response to the low frequency signals, and you're left with just the one that you want. To get rid of the high frequency signals, you use an inductor. To get rid of the low frequency signals, you use a capacitor. And by tuning the size of the inductor and the capacitor, you change where their sweet spot is, so you change your radio station that you actually amplify and listen to through your speakers. But they're all received. There's nothing not receiving in there. Yes. So, very good. So what you're doing is you're using the radio frequency of the station as your driving frequency, and you're setting up the natural frequency of your circuit by using the capacitor and the inductor. And when the driving frequency matches the resonance circuit, that matches the circuit of your radio, you get resonance in that circuit, and so the signal is amplified. So you use an amplifier after that to make it bigger, yeah. But that's resonance, yeah.
Do you think there are creatures that can hear things at such low frequencies that they can just hear every radio station going on?
Oh, radio station is very high frequency.
Oh, okay, well then, other than that, an animal like a dog or something that can hear a very high frequency. Have you ever heard of anything?
No, I don't do anything like that.
Well, yeah. Professor, with regards to what he's saying, I have heard that certain mammals, mice in particular, are able to hear the frequency emanated by electrical sockets.
Okay, cool.
I suppose there might be some possibility of that.
I mean, there'd have to be some mechanism inside the ear of inside the animal which would pick up that electrical signal. It's electromagnetic signal, so it's not sound. But yeah, okay. It doesn't really matter though, does it? So, I hate to be a jaundice, but it's like. We tend to use most of the capacitors in the world for tuning circuits and decoupling circuits. It's used in signal processing rather than power electronics. It seems to me the world of electricity is divided into power stuff like my brother does, power stations, motors, that kind of stuff. And there's the signal processing stuff, more the electronics type stuff. And you got to know which one you're getting into, because if If you want the electronic stuff and you go with electrical engineering and it's a traditional electrical engineering program, you learn how to run a power station, and you know, you've got to be sure about which one you want. They're very different. Okay, so we have this thing called a capacitor. It's basically, if I really want to think about it, it's a charge storage device, but really what I'm doing is I am creating inside here, lost my pen again, I'm creating an electric field. And the electric field is what stores the energy. Okay? So it's about the gap and the electric field in the gap rather than the plates, although we tend to talk about the plates. The plates are used to create an electric field in the gap. So, okay, so we say capacitor's capacitance is the magnitude of the charge stored in one plate of the capacitor per volt potential difference applied across the capacitor. We need a figure of merit for how effective, how capacitance if a capacitor is. And what we say is that our capacitance, which is measured in farads, is equal to the charge stored, which is measured in coulombs, divided by my potential difference, which is voltage. I tend to use two terms, EMF and potential difference. And they're both voltage measures. The EMF is the voltage of your power supply, and the potential difference is the voltage drop across your components. It's a bit like the water pump creates a water pressure difference, and the straws support a water pressure difference. The straws don't create pressure, you need a water pump for it. So, although it's all measured in voltage and what you create, you spend, we refer to the voltage that we're creating as the EMF, and we refer to the voltage that we're dropping across our components as the potential difference, but it's all measured in volts. So, how much charge can a 7 picofarad capacitor hold when a 4 millivolt potential difference is applied across its terminals? So let's just draw this out. Let's do that. And then the symbol for a capacitor is kind of intuitive. It's just basically two parallel plates. Oh, I didn't mention the fact that sometimes capacitance exists when I don't necessarily want to create it. So we have to know about capacitance even if we're not deliberately making capacitors, because it can affect our circuits and the like. So sometimes I have to be careful about that. But when I'm deliberately making it, however, the symbol for a capacitance is two parallel plates. This is the positive terminal, this is the negative terminal. And this here, we said was 4 millivolts, and this here, we say how much charge can it store, and this is 7 picofarad. So this is a kind of exercise in a couple of things. So capacitance equals the charge over my potential difference. That's its definition. You can say capacitance is defined as that. And today I want to know how much charge is stored. So capacitance is, so charge is equal to capacitance times my potential difference. So I'd say my capacitance is equal to, I'd say my charge is equal to my capacitance, which is 7 times 10 to the minus 9, because it's pico. And that's 4 times 10 to the minus 3, because it's milli. So,
Pico's 12.
oh, pico's 12, yeah. Oh, don't tell anybody I did that, man. Especially those physics 1 people. Thank you. So that's going to be 28 times 10 to the minus 15 coulombs. And if you want, you can figure out that that would be 28 times 10 to the minus 15 over 1.6 times 10 to the minus, how many, what's the charge of an electron? Can you remember? 10 to the minus 19.
You learned that in this class?
Yeah, yeah.
Oh, I don't.
First chapter. So that's going to be whatever that works out to be, electrons. You know, a coulomb is a massive number of electrons. Massive number of electrons. It's huge. A lightning strike might be, might involve, if you took the amount of charge given by a lightning strike, it could be, I don't know, 10 coulombs of charge comes to ground, you know. It's a massive amount of charge. Massive amount of electrons on that. Okay, so we have that, and then which trace best represents the relationship between the charge on a capacitor and the potential difference across the capacitor? So C is defined as my charge over my potential difference. And I want to do charge, so charge is equal to C times my potential difference. And what I find with this is, people often kind of like struggle with these things, and there's really, there's not that much need. So look at your expression. I want charge, which unfortunately has the C symbol behind it because that's the unit, and I have potential difference, which has the V behind it, which is like, well, what we call voltage anyway. So there's my delta V, and here's my charge. And so many people can see, well, that's linear. It's Y is equal to slope X delta V plus C. Yeah, it's X, yeah, plus B. It's just a linear expression. And so they'd, well, is it B or is it D? And you say, well, as voltage goes up, my charge goes up, so it's going to be D. Yeah? So some people can see it. Some people can't. And for that, what my suggestion is, you're going to go delta V, and you're going to go 0, 1, 2, 3, 4, 5. And you're going to go, well, let's C equal 1. It's a constant. It's capacitance. Why call capacitance 1 farad? It makes life simple. I have 0 times 1, which equals 1, and 1 times 1, which equals 1, and 2 times 0 times 1, which equals 0, and 1 times 1, which equals 1, and 2 times 1, which equals 2, and 3 times 1, which equals 3, and 4 times, etc. And then I get this, and I go, well, I want voltage, and I want charge. And I'm going to give you just a grid box. This is a skill I want you to start developing. With no numbers. And you say, well, look, I went from 0 to 5, 0, 1, 2, 3, 4, 5. I went to 0 to 5 on the voltage. And what did I get? I got 0 to 5, 1, 2, 3, 4, 5 on the current, on the charge. And when 1 was 0, the other one 0, and 1 was 1, 2 went with 2, and 3 went with 3, and 4 went with 4. That. So the immediate skill is, if I give you that pattern, can you recognize which wood is it? Is it A, is it B, is it C, is it D, or is it E? And then the secondary skill, which I'll bring in, is if I give you that same question and just give you that grid without any numbers, can you plot that graph out? A graph out. And people say, but you didn't tell me which numbers to plot. And I say, yeah, I didn't. And one person might choose 0, 1, 2, 3, 4, 5 for the x-axis. And somebody else might say 0, 5, 10, 15, 20, 25 for the x-axis. And somebody might say 0, 2, 4, 6, 8, 10 for the x-axis. And then somebody might say, well, I'm going to assume that my capacitance is 1 farad. And somebody else might say, I'm going to assume it's 10 farads. It doesn't matter, it's the same for all of them. I'm going to assume it's 5 farads, it's the same for all of them. And then you're going to get your answers. And what's going to happen is you're going to get different straight lines. But I can figure out that you're getting a straight line from it. You put down the numbers, I can work with it. So I look at the ratios and the like. And yeah, it's a little bit more tricky for me to grade because everybody does something slightly different, but I can figure it out. And what that tells me is, are you still kind of just solving problems where you're given everything apart from one answer? Or are you able to think about these things graphically and from equations and the like? It's a good skill to have. Because life doesn't tell you how far to extend the x-axis and how far to extend the y-axis when you're doing something on a building site. You've got to figure it out. You've got to say, well, we're going to go 20 feet or whatever. So getting you to feel more comfortable in choosing your own numbers, I think, is a useful thing to. You'll never get a lot of questions on a test like this. You won't get like all the questions are like this with one numerical value. There are always going to be more numerical values than this, but I think it's a useful skill. So here's a parallel plate capacitor. This is the classic one. It's two parallel plates. Most common type of capacitor is a parallel capacitor. It consists of two parallel conductors that are isolated from each other, isolated by a gap, or isolated by a piece of wax paper, or isolated by a thin oxide, or isolated by some nasty chemicals. Could be a wet solution with a thin oxide that you grow, all that kind of stuff. One plate can be charged positive while the other is charged negative. The capacitance of the parallel plate capacitor depends upon its cross-sectional area and perpendicular gap. So the gap is between the plates. And the cross-sectional area, in principle, it is the cross-sectional area of the gap. So if I were to take a plate like this, and rather than having my second plate parallel to it, if I was to slide my second plate like that, so that the actual parallel bit was like that, so there's the parallel bit. So I've only got a little bit of a gap. This bit's just a plate by itself, and that bit's just a plate by itself. Then I have a very low capacitance, because it's not the area of the gap, it's not the area of each plate. It's not the area of one plate particularly, it's the area of the overlap, the gap of the overlap. So watch out for that. Capacitance of a parallel plate capacitor depends upon its cross-sectional area and perpendicular gap size. The relationship is capacitance is equal to epsilon naught A over D. So what's going on here? You can figure this out. If it's about charges, then what's going to happen is, as I apply a voltage to this plate, I'm going to get to the stage where the charges are so close together that the field is so strong that my battery can't push any more charges on there. Does that make sense? And then I stop charging up. I stop charging up. Well, the charge proximity has to do with how many charges I have and how big the area of the plates are. So if I just simply make this plate bigger and make that plate bigger, well, now my charge is spread out and they're not so close together, so the field is not so strong, so I can add more charges. So basically I can, if you like, I can extend my parking lot. If I've added more charges, remembering that capacitance equals charge over delta V, if I've added more charges for a given potential, I have increased my capacitance. So as my area, cross-sectional area goes up, so my capacitance goes up. So put area on the top. Now, for my gap, this is a bit harder to see, but I can justify it like this. If the capacitance was not affected by the gap, I'd make them as big as I wanted. You know? Well, I know that can't be right because I make capacitors kind of narrow because I want a big capacitance. Alternatively, probably the better way of explaining it is that my electric field is equal to my dV by dx. So if I make if for a given electric field, if I reduce my gap, I get a bigger electric field. And bigger electric field means more capacitance. But I've not really linked electric field with capacitance here. Okay, so let's think about it. If the gap is bigger, then it must affect the capacitance, and if it doesn't affect the capacitance, then I might as well have as big a gap as I want, so logically that doesn't make any sense. If as the gap gets bigger, the capacitance gets bigger, then there's a metal plate on Pluto, and there's a metal plate on the Earth with a huge capacitance between them because the distance is phenomenally big, and that can't be right. So it makes sense that as the gap gets bigger, so the capacitance gets smaller. It might go as an inverse square, or it might go as an inverse, and I don't know enough at the moment to decide. So I've got to have a little bit of memorization here, and it goes as an inverse. That comes out of the theory, okay? So the capacitance increases with area and decreases with separation. But it's not equal to that. Area is measured in square meters, D is measured in meters. If I'm working in inches, square inches and inches, it's different. If I'm working in centimeters and square centimeters, it's different. I need to have a constant proportionality. And so I have this thing, and this is called epsilon naught. We saw it before in Gauss's law. It's basically the permittivity of free space. It's just a standard constant. I tried to show you this during the lab, and it failed abysmally, and that's a bit surprising because previously I've been able to show it with the same equipment. Oh, actually, I used the demo equipment before, but I'm still surprised I couldn't see it very well. And that is if I fill the gap with other stuff, not vacuum, not air, then I tend to get a magnification of the capacitance. I can't fill it with a conductor, of course, or else I'll just get current flow. So I've got to fill it with an insulator. And I'd like to try and justify that to you. And I think I can. And we'll go like this, and we say, okay, imagine that I just have a parallel plate air-filled capacitor. What's going to happen is that battery is going to push a positive charge on here and a negative charge on there, and then another positive and another negative, and there's a field now developing, another positive and another negative, and another positive and another negative. And let's say that's all I can do. This next positive wants to go up here, but it can't make it because all these guys are going electrostatically, get away, get back, get back, get back. The battery's pushing them up the wire, and that plate is pushing them back. And now we're in equilibrium, so they're not going up the wire anymore. They're all sat there. Same goes on the negative side. Okay, that's a fully charged capacitor. That's what happens with a fully charged capacitor. If I increase the voltage, I push more charges on. If I decrease the voltage, more charges get pushed back. Now let's put an insulator here. Now an insulator is just a neutral atom. We can think of it as being a positive and a negative superimposed on each other. Yeah. The center of charge for the negative cloud is superimposed upon the center of charge for the positive cloud, even though the sizes are different, you know. But there's an electric field through here, and what that does is that electric field attracts the positives. I'm going to draw it a bit weird now. I'm only going to draw one of them. It attracts the positive part of the atom to the negative end, and it leaves behind or attracts the negative part to the positive end. That's what the electric field does. It tends to spread out charges like that. I'm exaggerating, of course. Now, if you think about it, well, these negatives are kind of close to the positives, and these positives are further away. So because of the inverse square relationship, or the inverse relationship because of the field, we can maybe cross out one of these guys, maybe two of these guys. Not that they're not there, but the electric field associated with them has been somewhat neutralized by those. Yeah? So when you're in this wire and you're looking, you don't see 4 positives now. You see in 2 positives. There's 4 positives, but these 4 negatives a bit further away. And the sum is like having 2 positives. Yeah? So now, in that case then, I can add a couple of extra positives on there. because it's a field of 4 that pushes back. And if I look on this other side, same story. I have, well, these 4 positives kind of cancel out 2 of these negatives. They're still there, but it's like the field associated with them has been balanced by these 4 positives. And so these negatives that are in line waiting to get on kind of go, oh, there's only 2 of them there now, so I can add another 2. So I've just increased the amount of charge, and so by definition I've increased my capacitance, because my capacitance, of course, is equal to the amount of charge you can have on the plates for a given potential difference. I didn't change my potential difference of my battery, but because I had that polarizing molecule or atom in between, I was able to put more charges on it. Cool. So K is a figure of merit, and it's always bigger than 1. Well, no, that's not true. You could say K for air is 1. You could say K for a vacuum is 1. And then insulators are more than 1. You might actually be able to get... That's interesting. I wonder if you could get something really weird which would have a K which is slightly less than 1. It's not a useful dielectric as far as we're concerned. So think of dielectric constants as being from 1 and above. And you're getting free capacitance. It's like you put a piece of paper inside and you're getting a better capacitor out of it. And what's more, you can use the paper as a gap creator. Trying to get 2 parallel plates that are not touching is incredibly hard. So put a piece of paper between them and roll them up. And you have a really nice capacitor. It's brilliant, really. It works really well.
Professor, concerning that with the dielectric, so the more insulatory a material is, the greater the capacitance?
I didn't say that. I just said the dielectric constant of the material. You need an insulator. You can't have a conductor, or else it's going to conduct across the gap. I don't know that the dielectric constant of a material is related to its insulation properties. I don't know that. It's to do with the shape of the molecule and the shape of the atom and all that kind of stuff. Not the shape of the atom, but it's to do with the construction, the structure of the thing. So I'm not sure it's a one-to-one relationship. Maybe other people know it's true, but I don't know that for sure. So, what we say is dielectric is a non-conducting material such as rubber, glass, wax, paper. When it is placed in the gap of the capacitor, it increases the capacitance of the capacitor. We put a K in, which is the dielectric constant. The capacitance of the filled capacitor is greater than the empty capacitor. All dielectrics have a maximum electric field strength that they can support. At a voltage greater than the dielectric strength, the dielectric begins to conduct. You get basically a zap going through. You basically ionize those molecules, those atoms. You get a conductive path from one plate to another. When I was a student, I did some work where they had an aluminum base with a very, very thin, maybe 100 angstroms, which is 50 atomic layers thick, and then a gold pad along here. And for these so-called metal insulator metal devices, which are basically capacitors, you can get some very interesting electrical properties. They have switching properties, and at one point they were actually rivaled semiconductors. And when I first came to the States, I was when you first come, the people you work with kind of like you're like a tourist, so they take you everywhere. So this one particular person was interested in sailing, so they took me sailing one day. And I was talking to some other people at the sailing place, and this guy said he was a retired engineer, and I said, oh, what do you work on? He goes, well, I worked on something you've probably never heard of, but it rivaled semiconductors. And I'd heard that kind of turn of phrase before. And I said, you worked on metal insulator, metal devices. And he looks and goes, that's amazing. They've not been studied for 15 years. Semiconductors got rid of them. And I said, I think I was the last person to ever work on metal insulator, metal devices. And it turned out I wasn't, because when they did the long exposure facility on the space shuttle where they wanted to count the number of they wanted to count the number of dust particles in near Earth orbit. So they put up metal insulated metal devices, and every time a piece of dust zapped it, you'd get a little zap or through the surface, and you get a little electrical, like it would go dust particle, dust particle. You could count them electronically. So it's very interesting. Well, I found it interesting. How big is the gap between the parallel plate of a circular air-filled 3 microfarad capacitor with a radius of 4 centimeters? Man, I'm being a real, what can I say? I'm in a rotter with this. 4 centimeters, and it's, how big is the gap? So D, and it's microfarads, 3 microfarads. C is equal to 3 microfarads. And what else? I've got that. I've got a circular, okay. So let's have a look. Capacitance is equal to K epsilon naught A over D. I know it's air-filled, so let's rearrange this to get what I want. D is equal to K epsilon naught A over C. My K is 1. My epsilon naught, oh, trust me, I didn't give you it, and I don't honestly remember it, so let's have a look. Let me do a quick bit of research here. I should remember it. I'm a professional, but I don't remember it. So let's have a look. Let's go there. I'm going to put down permittivity, permit.
K, isn't it 1 over 4 pi epsilon naught?
Ah! That's, of course it is. So that's, so K, yes. So if K, E, is equal to 1 over 4 pi epsilon naught, that means that epsilon naught is 1 over 4 pi times Ke. Yep. So this is going to equal 1 over 4 pi times 9 times 10 to the 9. Is that not Ke?
It is.
Yeah. And Ke, so I did that bit, and then my A is pi times r squared, and that's going to be 4 times 10 to the minus 2 squared, because it's centimeters, over my capacitance, and my capacitance is 3 times 10 to the minus 6. Man. So my D is going to equal, well, my pi's cancel. And that's going to be 16 times 10 to the minus 4 over, that's going to be 27 times 10 to the 3, which equals, what is that, 16 over 27? Did I bring a calculator? Yes. 16 divided by 27, so that's going to be 0.59 times 10 to the minus 7. So that is, it's 5.9 times 10 to the minus 7, which is 6 times 10 to the minus 7 meter. 6 times, I'm sorry, 10 to the minus 8. I make that 10 more, so I make that 10 less, which is 6 times 10 to the minus 8, which is D. Can you see from a teaching point of view? So I do want this a bit more challenging, just to be like, you know, part of the family. But all our attention was about the prefixes. Wasn't so much about the equation. And that's why that old joke about the questions he does in class are the simple ones, the questions he asks for homework are the next harder ones, and then the ones I get on the test are the most difficult. That's a kind of natural consequence of teaching. It's a good way to do it like that, actually. If I keep showing you all the difficult ones, then you don't get the general feel of it. You just kind of go, man, that was hard. Man, that was hard. You know, so there's a certain charm in that. So we know how to calculate the value of a capacitor from its physical properties. Supposing that I don't have a capacitor of the size that I want, supposing, you know, nature or life just adds these things up and makes circuits out of them, then how do I combine them? And basically, there's, I can kind of talk you through this. Can you see how that piece of metal is basically joining that guy to there and joining that guy to there and joining that guy and joining that guy to there? So it's like I have those 3 plates touching each other on top and those 3 plates touching each other at the bottom. All I've done is I've increased my area. Agreed? If I increase my area, I make my capacitance bigger, don't I? So if I have C1, C2, C3, and I want to make them bigger, add them together. I can prove it by this, the charges, but basically just intuitively. I just add them together because I want a bigger capacitance. By the same token, can you see how that positive plate must be at the same potential as that negative plate? And all the positives on here must be cancelling the negatives on there because they're touched by a piece of wire. So I could basically take that negative plate and slide it down, and there's the gap. And I could get rid of these pieces of wire in between, so it will look like that. I'd have my red and my blue, and my red, and then my blue, and my red, I forgot one, and then my blue. So I'm basically touching these 2 guys together, and they go away, and these 2 guys together, so the first 2 are there, then 2 are there. And then I can just slide these things out. So I end up with a capacitor which is the same area, but a bigger gap. Oh, it must have a smaller capacitance. How can I make a smaller capacitance? 1 over the capacitance in series equals 1 over C1 plus 1 over C2 plus 1 over C3. 2 classic equations. Yeah.
Would you be so kind as to remind us of resistance in a series circuit?
Opposite.
Yeah, opposite. Okay, that's what I thought.
So what I learned to do is, you learn one of them. I learned resistances because it's what I was introduced to first. And then I learned that capacitors go the opposite way. And you know, if you've not learned resistances, then you might want to learn capacitances and then say resistances go the other way. But it is the opposite, so you've got to be careful about that. In series, capacitors get less. In parallel, capacitors get more. What is the equivalent capacitance of a network that consists of 3 nanofarad capacitors, a 3 nanofarad, a 4 nanofarad, a 12 nanofarad connected in parallel? So parallel, let's just talk about that for a minute because we've not really talked about that before. Parallel is where your circuit, if you imagine a point of interest moving through your circuit, if you like the current, but sometimes there's no current flowing in a circuit. Imagine taking your point of interest. You get to this point here, you have a choice of paths. Whenever you get a choice of paths, you have a parallel circuit. If I add these 3 together, I'm trying to find the one that will replace them. If I add these 3 together, it's going to get bigger, so that reminds me that C parallel is equal to C1 plus C2 plus C3. C parallel is equal to, they're all nanos, aren't they? So 3 nanofarads plus 4 nanofarads plus 12 nanofarads is going to equal to 7 plus 12. That's 19 nanofarads. There's my answer. Because it got bigger. Let's take the same scenario and now this is series because imagine your point of interest. There's no junction, there's no choice. If current is flowing, the current will, all the current that goes through the first capacitor goes through the second, goes through the third. Yeah? So if you think about current doesn't flow through a capacitor, it flows to a capacitor and causes the opposite current, the opposite electron flow in the opposite side. So it's a bit more, but we can think of it as current flowing through for a while. So this is in series, so 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And again, notice it's 1 over. So 1 over C series is equal to 1 over 3 nanofarads plus 1 over 4 nanofarads plus 1 over 12 nanofarads. Can't I just add those up, can I? So this would be, let's have a look. This would be, common denominator is 12, so this would be 4 over 12 nanofarads. And this would be 3 over 12 nanofarads. And this would be 1 over 12 nanofarads. So 1 over CS is equal to 4, 5, 6, 7, 8. 8 over 12 nanofarads. So flip it over, and we're going to get C series is equal to 12 over 8, which equals 1.5 nanofarads. It got smaller. And it's smaller than any of the original ones. The 3 is the smallest. It's smaller than the 3. If you do this and you get a value which is in between the ones that are in series, you made a mistake. It's got to be smaller than any in that combination. Most common mistake is people, again, they don't think in sentences. So they don't write that down. They just write that second bit down. And so they work out their answer. They work out their answer, but they've not written that down, so they don't flip it. So they'll give me 8 over 12. They'll give me 0.66 nanofarads for the answer. So you've got to write down sentences. Don't write down little phrases and snippets. Write down sentences. They get a bit more interesting. So this is a bit of it's in parallel and a bit of it's in series. And this is a little bit like we did with circuits, where you've got to know where you got to know your way in. This is unambiguously in parallel with the 2 is unambiguously in parallel with the 4. But is the 3 in series with only the 2? Well, no, it's kind of in series with the 4 as well. So pick the unambiguous bit. And we just start off and you just do this. It's just a bit laborious. It's not, math is not hard. It's just laborious and it's easy to make a slip on it. So this would be 12 and this would be 3 and this would be 4 and this would be 2. And what I do is I say I'm going to combine these 2 guys together. And this is 12 and this is 3. And this is C parallel equals C1 plus C2. So this C parallel is equal to 2 plus 4, which equals 6. So I can and now they're in series, and I want to make those into just one big one, and I go C series 1 over C series equals 1 over C1 plus 1 over C2 plus 1 over C3. 1 over C series is equal to 1 over 6 plus 1 over 3 plus 1 over 12, which equals 2 plus 4 plus 1 over 12, because the common denominator is 12. So 1 over C series is equal to 8 over 12. So C series is equal to 12 over 8, which equals 1.5 farads. So it's not hard, it's just laborious. Again, the most common mistake is not flipping it or making a slip. Putting down CS is equal to 1 over C1 plus 1 over C2 plus 1 over C3, something like that. The trick is, the skill is picking out the unambiguous bit and then, going from there. Another version of this is there's a million circuits I could do, but I don't like to just have a million circuits. I like to give you some that are stereotypical. But I could do something like that where I have a series bit which is unambiguous, and then you add the series answer to the parallel bit. So you're doing it in the opposite directions and the like. Yeah.
Should that not be 12 over 7? 2 plus 4 is 6 plus 1 is
Oh, yeah, 7. Yeah, sorry. Yeah, 12 over 7, which is something else. Yeah. What is that something else?
1.7.
1.7. Good. Okay. Thank you. Yeah. Well done. Well spotted. Yeah. And I need more sleep, don't I? How are we doing for time? Because we've got a little bit to go. Okay. So let's get down to something that's a bit more interesting, really, which is, well, not more interesting, but it's different, and that is the energy stored inside a capacitor. And remember, the voltage is the joules per coulomb, so this is how energy is going to come in. We say consider charging up a capacitor. As the charge increases, the potential difference between the plates increases. So now let's think about this. I have a battery source, and the voltage across the battery, the EMF, is constant. But just because I connect 12 volts across the capacitor does not mean to say that I have dropped 12 volts across the capacitor. My potential, oh, well, it does. I'm jumping ahead of myself. Let me draw you another circuit. I'm rushing a little bit, and I'm making some mistakes here. In reality, every circuit has a bit of resistance in it. So just because I have 12 volts EMF does not mean to say that the whole of that 12 volts is applied across the capacitor instantaneously. There might be some across the resistor and then some across the capacitor. So I would see, if I got a voltmeter, I would see my voltage across the capacitor, the potential difference, increase in time because the charge takes time to get onto the capacitor. So if I plot my potential difference across the capacitor versus the charge on the capacitor, this is what I'd see. Now, if you think about it like this, well, why isn't it 12 volts immediately? Because you can never make that circuit. You're always going to make this with a little bit of resistance. It might be very quick. It might charge up very quick, but it's not going to be instantaneous. So do you see the distinction between the EMF and the potential difference, how useful it is to distinguish between those? So I get my little bit of voltage and my little bit of charge, and I start off with not much charge on it, so not much voltage, and it just increases as time passes. In the end, I get to the total amount of charge and the total amount of voltage, and this potential difference will equal my EMF. That's when it stops charging. Consider an instant when the charge on the capacitor is little bit of Q plus Q. The associated potential difference will be potential difference equals the charge over my capacitance. I'm just trying to think, when did I introduce that to you? I did initially, didn't I? I said the definition of capacitance is equal to the charge over the potential difference. So I just rearranged that. That's where that comes from. And then work, of course, well, if this is in joules per coulomb, and I multiply it by the number of coulombs, I get the numbers of joules. So work is just the little bit of voltage, the potential difference multiplied by the little bit of charge. And if I look across here, my potential difference is my charge divided by my capacitance multiplied by the little bit of charge. So then I say, well, the total work required to charge up the capacitor from nothing to big Q is the area under this graph where this is big Q. It's a triangle, isn't it? So it's going to be, the area is going to be half of Q times delta V. So it's going to be a half of Q times delta V, which is, well, okay, which is, let's just do it the way that we're supposed to do it. So work equals the integral from 0 to Q of my charge over C dQ. And C is a constant, so 1 over C comes out. So it's the integral of Q dQ. The integral of Q dQ is, well, you integrate, you increase the power by 1 and put it in the denominator. So it's 1/2 of big Q squared over C. So that's A amount of charge, that's the A amount of energy stored, delta U is equal to the work done, which equals this. And then I can substitute in, so 1/2 Q over C. Let's say, I'm going to use this equation over here. Let's say that I want to take one of those Q's and make it C delta V. So I'm going to get, Q squared, well, let's do this. Q times Q over C times 1/2. That's just written out again. I go, well, 1/2 Q. Let's take this Q and make it, let's take that Q and make it C delta V. I'm sorry, I'm rushing. So there's my Q squared over C. I want to, what do I want to do? I want to replace that C with a Q delta V. So I replace that C with a Q delta V. So those Q's go, I got rid of that, and I end up with a 1/2 Q delta V. And then I can do the substitution again, and I can replace that Q with another C delta V, so I get 1/2 C delta V squared. You can also get to these three by recognizing that the area under the curve is the work done, which is Q times delta V. It's a triangle, so it's half of it. So we came in here with theory, but we can come in here by recognizing a triangle. Either way, know or be able to get to those three values, those three equations. So let's stop there. Yeah, I've not got much more, but I got to stop there. No, let's. I'm going to do this. I'm going to cheat a little bit. So I'm running out of time. So what I did was I just basically wrote down my basic equation for my energy that I remember, and then using this expression for the definition of a capacitance, I substituted in until I found the combination I wanted, and the combination I wanted was C and Q. This was the guy here, so I just substituted into that, and I got my answer. And here's the second one. We just were given C and delta V this time, so I went through the same process. I wrote down the one I knew, I substituted in, this is the one I want, and I substitute in. I'm sorry if I have in 9 volts and 9 farads. I don't usually do the double up like that.